The Greater Metropolitan Manila area has a long history of natural disasters and extreme weather events. Following the calamity of Typhoon Ondoy in September 2009, which caused about 500 deaths and damage of about 41 billion pesos, the Greater Metropolitan Manila Area Risk Analysis Project was begun. Covering the 16 cities and 1 municipality of Metropolitan Manila, as well as parts of Bulacan, Cavite and Rizal, the study looked at the hazards of flood, wind and earthquake. The project is a collaboration between the technical agencies of the Government of Philippines, supported by the Government of Australia Aid Program and GeoScience Australia. The aim of the project has been to give a much clearer understanding of the risks from natural disasters, of where the risks are greatest, and of how the dangers can be reduced. This analysis identifies 3 main types of potential risk: flooding in the Pasig-Marikina River Basin, severe winds associated with tropical cyclones, and risks from damaging earthquakes from the West Valley Fault. Natural hazard risk analysis involves understanding the relationship between a hazard, the exposure or elements at risk, and the vulnerability of those elements. Risk can be expressed in terms of physical damage, economic loss, or the number of people killed or injured. Information was developed that first built an understanding of how people live and work in the Greater Metropolitan Manila area. The study area included the low-lying areas along Manila Bay and Laguna de Bay, the flood-prone Pasig-Marikina River Basin, the elevated areas in Rizal Province to the east, and the West Valley Fault, which passes north to south through the metropolitan area. LiDAR, light detection and ranging, was the first major set of data to be collected. An aircraft flying over the Greater Metropolitan Manila area used a special laser scanning device to measure the profile of the landform and the heights of such features as trees and buildings. From these measurements, a digital elevation model, or DEM, was constructed. The model gives us an overview of an area that is home to about 12 million people. But where do they live? Where do they work? And what makes them vulnerable to natural hazards? Using the best available data from many sources, a picture of the built environment is developed. Of building density, of population density, of the current land use, of building heights, and of the complex mixture of the age and type of buildings that are present across the metropolitan area. All of the information about the characteristics of exposure that are needed for risk analysis have been gathered and organised into a spatially enabled exposure database. To estimate the vulnerability of buildings exposed to natural hazards, engineering models for different building types were developed. Not all buildings will experience the same level of damage when they are exposed to the same level of hazard. For example, engineered reinforced concrete buildings will, on average, suffer less damage than unreinforced masonry buildings when subjected to the same level of ground shaking. Hence, vulnerability models were developed for different building types to characterise the average economic loss for each building type. Economic damage is complex. Low-cost buildings may be destroyed and be inexpensively replaced, but high-cost, well-constructed buildings may suffer minor damage that is relatively expensive to repair. All of this is reflected in datasets estimating the costs of damage. The relationship between wind and the landscape changes the impact of severe winds on the city. Winds increase in ferocity as they flow over hills, over ridges, and over high ground. Areas such as the open space of the airport, of Manila Bay, and of the riverbanks experience higher wind speeds than built-up areas. Knowing wind strength means knowing how buildings, billboards, and shanties will be affected. The areas of greatest damage can be seen in the mountainous regions in the east and along the escarpment of the West Valley Fault. The steep topography in these areas, combined with the presence of wooden and makeshift structures in the rural areas, are the reason for the high level of damage. Flood projections are calculated from known rainfall figures. Metro Manila has experienced catastrophic flood events along the Marikina Valley and the San Juan River and can expect more. The figures that have been calculated show that there is a possibility of a flood bigger than has been experienced in recent times. The results also show how damaging floodwaters can be expected to move through the city over a period of 48 hours, how high floodwaters will reach, and what the area of inundation will be. Damage is widespread in low-lying parts of the city and adjacent the main river systems. A particularly large damage hotspot occurs in the city of Marikina, where deep floodwaters combine with a high proportion of wooden and makeshift structures, which are easily damaged by flooding. As with winds and flood, the mapping of earthquake events can be related to what is known of land use, and physical and economic damage can be mapped according to where the most fragile forms of housing have been constructed. The population affected can be mapped, and so can the economic damage because of the land use and construction methods. A range of earthquake events were used as the basis for calculations. The hotspots, clearly seen following the West Valley Fault, and areas lining Manila Bay, both the expectation of strong shaking and the high concentration of easily damaged buildings explain this. Risk analysis is employed for locating the areas at risk and quantifying the risk posed by earthquake, severe wind, and flood. We can illustrate this with the example of earthquakes by combining information on the three parts to risk and plotting the quantity of risk. By comparing formal settlements, major commercial areas, and informal settlements, we can see how the measure of risk changes. The factors considered are hazard, which describes the likely intensity of an earthquake in that area; exposure, which describes the number and type of buildings that may be at risk to earthquake; and vulnerability, which indicates the expected physical damage and economic loss, which varies from high for makeshift structures to low for reinforced concrete buildings. By identifying those places at greatest risk, we can highlight areas where, for example, modifications to land development or building practices would have most value. By identifying the most at-risk areas, local government units have the opportunity to adapt their planning in new developments and identify those places which, being most at risk, will need early warning of flood danger, early intervention, and assistance. The data products that have been produced by the Greater Metropolitan Manila Area Risk Analysis are free and will be readily accessible from the Office of Civil Defence and the Philippines Geo portal. They will be provided to each local government unit, which can update the data and build their own database for planning, designing and implementing projects, mitigation activities and contingency planning. Flood, earthquake and severe winds will always be a threat to the Greater Metropolitan Manila area. The risk analysis tools help us to understand, prepare for and survive these hazards. Australia stands ready to support the Philippines in this effort. By jointly investing in building the resilience of communities to natural disasters, we can contribute to a safer future for all Filipinos.